So I think we are in time, so let's do this. First of all, my name is Diptanu. As John was saying, I work on the Nomad core team. I'm an engineer in the core team. And before HashiCorp, I was working on Apache Mesos at Netflix, working on schedulers to run containers on the public cloud. So thanks to the organizers of HashiCon for giving me the platform to speak about Nomad today. And it's a really exciting day for us, for the Nomad team. Last year at HashiConf, around the same time, Nomad 01 was released. And today there were like 3 good talks of Nomad already. So it's a really great day hearing about Nomad used in production at scale. So you're at HashiConf. I'm not going to go over what the company does or what the tools that we make. I'm going to jump straight into the talk. This talk is going to be about the ongoing work we are doing in Nomad to make it a great platform for running stateful applications. I'm going to introduce to you a feature that we are calling sticky volumes. It's going to be coming out with the 0.5 release. And I'm also going to talk about like what we are going to do in the future related to disk and persistence and so on. So most of us in the infrastructure space are fighting the good war of making infrastructure useful and agile and making infrastructure very reliable. Over the last 2 decades, I think we have seen massive evolution of the tools and practices in the web operations space. We have transitioned from running scripts to automating provisioning of operating systems on individual servers using Chef and Puppet. And as we go beyond deploying to tens of hundreds of servers to tens of thousands of servers across multiple regions and data centers, we are going on deploying clusters and no longer deploying applications on individual servers and debugging entire clusters, the landscape of infrastructure automation and cloud orchestration has changed dramatically. Cluster schedulers are becoming the tool of choice for operators to manage clusters, and they're the last mile in the application developers' continuous delivery pipeline. And the challenges that the schedulers are solving for us are faster turnaround times, providing higher availability, and a single glass of pane to do operations across clusters and data centers. And this is where Nomad comes in. Nomad manages resources across clusters in multiple data centers and regions, and it provides an API to the application developers to run clusters of their application on those resources spread across multiple data centers and regions. So in a way, you can call Nomad as the kernel of the data center, where it provides all the API for supervision of clusters. So I'm not going to go very deep into how Nomad works and everything that makes Nomad like a good cluster scheduler, but I'm just going to highlight some of the high-level points so that like we have some basis from where we can discuss the newer concepts. So we built Nomad from the get-go to provide a really good out-of-the-box experience. We saw that the current schedulers have a high degree of operational complexities. Nomad was designed to be operationally simple. It needs no moving parts like etcd or Zookeeper. It's multi-data center and multi-region from the get-go, since running services across regions, across cloud providers, across data centers is becoming the new norm. It supports Linux, Windows, Darwin, and work is going on for supporting FreeBSD. It is built to scale to hundreds of thousands of cores. You probably heard about some of the scale that people are running Nomad on from Citadel's talk, and I think one of the earlier talks talked about like the C1 million challenge that Nomad did. So we were able to run like millions of containers on Nomad very consistently at a high throughput. Another key feature of Nomad would be that it's simply not a Docker scheduler, right? Like most schedulers come with the constraint that they're going to schedule containers. So Nomad is not just a Docker container. In an enterprise, you're probably not only going to be running containers, you're probably going to running like Java binaries or static binaries if you're using Go. So with Nomad, like you can schedule not only containers, which is like powered by Docker, but you can schedule like Rocket containers, or you could schedule simple Go binaries or Java jars, and Nomad would provide isolation and quality of service and other things that you expect out of containers. And users will be able to write even custom drivers when we expose the internal client APIs to plugins in the future releases. And like most technologies, Nomad is based on all the good research that has happened in the web infrastructure and data center scheduling space. It's heavily inspired from Google's Omega. Nomad is optimistically concurrent, allowing it to make scheduling decisions across many servers. It uses internal state coordination, so the same kind of internal state coordination that console uses, Nomad uses it internally, and so you don't need any external tool for high consistency of the state of the cluster. Some of the users need some of the existing schedulers needs user to build schedulers. Schedulers which are like two-level schedulers or orchestrators which don't come with a great scheduler by default. So users have to write their own schedulers, but we saw that users are plainly writing like schedulers which are of service nature, or like users are writing schedulers to deploy batch applications or cluster-wide applications. So we decided that we want a really good scheduler from the get-go. So we wrote highly optimal schedulers for running batch processes, for running service processes, and system workloads across the cluster. So Nomad comes with them by default. There is no additional need of writing custom schedulers unless you have very domain-specific needs. So let's talk about the API that Nomad provides to an application developer. So Nomad exposes a very simple interfaces, and the primary interface would be a job file written in a human-readable configuration language called HCL. The job file expresses an application's executable file or image if you're running containers. Its configuration details like environment variables, secret keys, resource asks, and it encapsulates details like placement constraints or environmental constraints. Like in a job file, you can say that I want to be running these jobs across data center A and data center B, but I don't want these jobs to be co-located together, so I want distinct hosts. Or like you can say that I want to be running this job only on a Linux version with the kernel of say kernel 4x or kernel 3x or something like that. So a job file is the API which basically the application developer uses to describe like what the application is going to be. And from there on, it's basically Nomad's job to scale the application and run the application across a cluster of compute nodes, which can be spread across DCs and regions. And once the application is deployed, Nomad strives to provide all the tools that an application developer needs to operate the application, like introspecting logs or looking at operational metrics, or even like if you're an operator and you want to drain a node because the node is not performing well, or the Docker daemon is not working well, or some other issues with the file system or something. So Nomad provides all those tools and APIs for operators to operate on the cluster in its entirety. So everything that users and operators would do with SSH, Nomad would actually like give an API for the users and operators to interact with the cluster scheduler and manage the applications that are running, manage the nodes that are running. And here is the timeline to all the features that we have shipped since Nomad was released in HashiCorp last year. And some of the important features are listed here. We did batch scheduling, we did system scheduling, we did restart policies, console integration, and we did runtime stats. And with Nomad 05, we are shipping Vault integration, TLS, and sticky volumes, which this talk is about, and disk watchers and things like that. And all these features were developed with one key objective in mind, to make Nomad an ideal platform, a really great platform for running stateless applications. We wanted to get the fundamentals right first before we tackle the harder problems. And we wanted to develop the core features, which is going to run like 70 or 80% of the workloads that enterprises have to run today. And so we focused on stateless applications. And having said that, all the changes starting from this release, like things are changing from this release onwards. We are going to focus on making stateful applications as well as stateless applications great on Nomad. So with that, our primary objective is that like from now on, we want to develop features and deliver features which would allow users and operators to run applications like databases and caches really well on Nomad. Before we go into that, like let's talk about like what happens behind the scene when a Nomad job is run. So a job constitutes of multiple task groups, and a task group is a single unit of work that gets scheduled on the cluster. So if you're running like a MySQL server and a co-process which backs up data to S3 from your ephemeral disk, that would be like a single task group, and Nomad would schedule them together, and task groups are materialized on the clusters as allocations. And an allocation is basically nothing much other than a running instance of a task group. They are ephemeral in nature, and allocations manages the life cycle of tasks, and it supervises the tasks, updates state of the tasks, and it provides like a shared file system. So when a task group is basically scheduled on a cluster, from there on, like, you are always going to be interacting with an allocation. Like, you are going to be asking yourself, how's my allocation running? Is my allocation running? On which node an allocation is running? What is the state of an allocation? And so on. So as allocations are a single unit of scheduling on the cluster, the allocation resources are divided into two parts. One is the task resources, the resources which are basically allocated to every single task of the allocation, and then there are some shared resources. So the task resources would be CPU shares and memory and network ports and network IPs. So these are resources which are allocated to every single task because we wanted to ensure a high degree of quality of service. So for example, if your task has been guaranteed certain amount of RAM, we will make sure that the application is getting that much RAM. On the other hand, disk resources are shared between all the tasks, and there is a good reason why we are doing it. For example, in the previous example that we talked about where you're running MySQL and a co-process, which is backing up the data that MySQL is running onto the disk, the co-process needs to see the file system of the original task. So then having a shared file system or having some shared volumes between the two tasks or multiple tasks in an allocation really helps. So every allocation, as we said, has a common shared file system, and we call them allocation directory. And allocation directory is where the shared data of all the tasks lives, and all the standard out and standard R log streams of every task is going to end up in the allocation directory, in the log directory of allocation dir. And every task is also going to have their own task directory. So this is how it looks like. So you might have a machine with a lot of ephemeral disk, and then on that node where Nomad is running, there will be like one or more allocation directories. And every allocation directory will have like task dirs. So if you have some application which is running in a task, and it doesn't want its data to be visible to the other tasks in the allocation, that application is going to be writing data in the task dir. Whereas if you want the application for the application to make the data that it is writing visible to the other tasks, then it would basically write those data in the allocation in the shared directory. So this is how the allocation a single allocation directory looks like. So based on what kind of driver you are using, so we have the concept of multiple drivers. So you can use Docker driver, or you could use raw exec, or you could use an exec. So these are different drivers. So the file system isolation would vary between different drivers. So if you're running an exec driver which provides higher isolation than, for example, the raw exec driver, what the driver would do is it would put every task in the allocation in its own chroot, and every task is going to see only its own task dir and the shared allocation directories. But it won't see the task dir of the other tasks in its group because they are living in their own chroots. So not all the drivers behave like that. The example that I gave is like from the driver which does the highest amount of isolation. So what are allocations? So allocations are pretty ephemeral in nature, right? So an allocation is basically like multiple running tasks. And when they are restarted, as I said, they're ephemeral. They will be restarted by the scheduler on a different node, and the allocation directory will not be preserved when the allocation is restarted, even on the same node. And once the the processes in the allocation moves into terminal state, the Nomad client garbage collects the data that the allocation writes. This makes running applications like Cassandra really hard, since updates to an allocation which needs creation of new allocation, makes makes a new allocation directory, and you lose the older data. Users in the community are always very smart, and they try to make the most out of the existing features that are available. So we have heard people running like running Cassandra with techniques like constraints, so that when an allocation is restarted, it lands on the same machine. Like people would basically add names to clusters, and they would add like a constraint in the job so that all the Cassandra instances are getting always placed on the same set of nodes, so that they're not jumping from one node to another and things like that. But this is not optimal. Like we don't want our users to be working around the features that we have shipped. And we wanted use cases like running Cassandra or running caches, where you might have data locality like a first-class concern of Nomad. So with that, we decided to introduce a feature called sticky volumes. So with sticky volumes, the scheduler prefers to restart the allocations on the same node. So for example, imagine you have an Cassandra or like a MySQL allocation running, and then you want to change like the environment variables or something like that. With sticky volumes, Nomad is going to prefer the same node where the allocation was previously running, and if it finds enough resources to run on the same node, Nomad is even going to move the existing data from the older allocation directory to the newer allocation directory. So if you're running MySQL, where MySQL is writing data to disk in forms of bin logs or write-ahead logs and things like that, when the allocation is restarted, the same data that the previous allocation had written would be available again to the new allocation. So that's much better than what we had before. And again, if Nomad cannot place the application on the same node, Nomad would replicate or migrate the data that the previous allocation had written on the node to another node over the network. So for example, to give you an example, say for example you are running Redis, right? And you are running 5 Redis instances on a node, and you want to resize the memory of one of the Redis allocations, or you want to give the Redis allocations more disk space, and now suddenly like we can't fit all the containers or all the tasks on the same machine anymore. So in that case, Nomad is going to move the allocation on a node where disk is available and memory is available, and since the allocation was marked as sticky, Nomad is going to migrate all the previous data from the allocation from that node to another over the network. So those, I think, like are going to help running more types of stateful applications on Nomad. One of the things to remember here is that replication is best effort, right? So what it means is that if the node disappears, the data will be lost as well. So there is no guarantee that the data is going to be moved. Data is guaranteed to be moved from one node to another only if the client is still available, only if the network is still available. For example, if you have a network partition and Nomad decides to reschedule the allocation on another node, and the new node cannot talk to the other node to replicate the data, migration won't happen in that case. It's not a streaming file system, or it's not a distributed file system. It solves certain classes of problems where you would be doing your own automation to migrate the data before restarting the application again. Sticky volumes, data migration of sticky volumes solves that purpose. So that's the design part of sticky volumes. That's the concept behind sticky volumes. Since 0.5, like we are going to be introducing a new configuration block in the HCL called the Ephemeral Disk. And in Ephemeral Disk, like users will be able to like turn on sticky, and they will be able to say that this is the amount of ephemeral disk that they need. And so this is how it works. So on a ephemeral disk, say you have an allocation directory with 2 tasks running, and if Nomad has to recreate the allocation because something has changed, like for example, CPU resources or memory resources have changed where the C group has to be created again or the isolation has to be created again, Nomad will prefer putting the allocation on the same node so that it can avoid migrating all the data over the network. In that case, the Nomad client is just going to move all the data from the existing allocation directory and task local directory into the new allocation directory. But if it cannot do, then what would happen is the new client is going to negotiate with the older client and tell that, hey, I am going to run this allocation, but I know that you have the allocation data of the previous version of this same allocation. Please give me all the data. In that case, the Nomad clients would do P2P replication and move all the data between them. And once all the data has been moved, the new allocation is going to start. And the data the data transfer that is going to happen between the clients are going to happen over TLS, and they will be compressed, and hopefully the protocol will allow to the operators to switch between different compression algorithms and things like that, because most compression algorithms has trade-offs, and you would use certain compression techniques in certain situations and certain in another, and other compression techniques in other situations. One of the other work that is happening with Nomad 05 is the concept of a disk watcher. So until now, Nomad was isolating disk, but Nomad was not accounting for the disk usage by the allocations. But from Nomad 05 onwards, if an allocation is using more disk resources than was allocated to it, the allocation is going to be destroyed or killed. And once an allocation is killed because of excessive data usage, the allocation will be transitioned to like a fail state permanently. Because when the allocation has consumed more data, even if you have marked the allocation as sticky, is not going to help, because the data when you have moved is going to be almost at par with the disk quota that the user had asked for. So there is no point restarting a failed allocation which has failed because of disk excessive usage of disk. So that's what we have on 05 with respect to the features of disks and persistence. The future work this is just the beginning, and in the future we are working towards volume plugins in the upcoming releases. There will be support for materializing additional volumes apart from the ephemeral disk on external services like EBS, EFS, etc. And API would be exposed over plugins. So this would help operators integrate Nomad with proprietary storage services as well. We are also working towards introducing file system drivers, which would allow users to use file systems like ZFS, Btrfs, etc. And this also plays an important part in the data migration. For example, depending on the type of file systems you might have, the migration algorithm can be different. For example, ZFS can do its own snapshot, so it would be easier to move data from one node to another, which has ZFS. Right now, the data replication that Nomad has uses custom framing protocols and so on. So allowing file systems and relying on file systems to do the snapshots and move the data around is going to allow higher levels of integrity, and it's basically pushing the problem down into the file system. So with that, I'm going to do a demo and show how sticky volumes work in practice. And okay. So people at the back, can you see the screen? Oh, okay. All right. Okay, good. Is it better? All right. Right, so basically the demo that I'm going to be doing is going to be 2 Nomad clients and 1 Nomad server, and I'm going to be running a Redis allocation. I'm going to be inserting a bunch of keys into the Redis allocation, and we are going to mark the allocation as sticky, right? And we will see what happens when node drain happens. So as an operator, you might decide that you want to take a node out of commission, and when a node goes out of commission, if the ephemeral disk was marked as sticky, the data is going to move along with the allocation from one node to another. So that's going to be the demo. So let's run Nomad here. Let's run it in client mode. So this is a little awkward. I didn't think about it. I can't see the screen myself. Okay, let me resize the screen a little bit. Okay, better. Minus config, vagrant, client1.hcl. So that's it. And oh wow, this is resizing the terminal too. Okay, and client2. All right, so started the clients, and let's see if this guy is in running as root. Oops. No, I think it was not running as root. Yeah. No, it's fine. Since some of the drivers needs privilege permissions, like since they're doing isolation and things like that, they need to run as root. Server 01. All right. All right. Opt go path, and then all right, so we started the server, and let's get a terminal and see all the nodes that are there to see if they're ready. And then we will run the job. So Nomad is, so when we design the CLI and the API of Nomad, we basically think of our users as two types. One is the application developers, and then there are like the server, the operators, like the operations people. So for example, if you're an operator, you can see what is running, which nodes are running in your cluster by doing this nomad node status, nomad editor, and then nomad node status. So it says that we have two available nodes. You can also see which servers are available. Nomad server members. So we have now a cluster of like 2 Nomad clients and 1 Nomad server. And now let's run a job file and see where this goes. So this is a job file that I'm going to show. Example. So in this job file, we are saying that run a task group which is called cache, and give me an ephemeral disk of which is sticky in nature, and give me 110 MB of RAM, 110 MB of disk, and then specifying the restart policies, and then I have a task which is basically nothing other than like a Redis server, and using the raw exec driver, and specifying all the configurations like the command to run and things like that, and providing an artifact source which is going to give us the configuration of the Nomad of the Redis server. So if you are in production, you would probably like have other means of shipping configurations. Like you can probably tarball your configuration, or like put configuration on a console key value server and whatnot, and then define like a service block for this Redis, so that like so that the Redis server is now then available to people who are trying to discover Redis over the network, and specify the resource asks for Redis, which is in this case 500 CPU shares and 256 MB of RAM, and then one static port, 20,001. So now let's go and run it and see what happens. So I'm going to run this using Nomad now, Nomad CLI again. So Nomad Run, example. So there you go. So now Nomad Run is basically saying that it created an allocation, and the allocation is running on a particular node. To do some introspection on the status of the node on the job, like we can use this Nomad status command, and it will go, and you can see like number of running allocations right now is 1, and it's running on a particular node. Let's connect to this allocation. Let's find out where this allocation is running, and use this Redis server and write some keys into it. To see an allocation, like this is the command alloc status. So you do nomad alloc status and then the allocation ID. You don't need to put the whole allocation ID. You can put like partial allocation ID if you don't remember the whole thing. And then Nomad is going to show you that the current task resources. So it's showing that out of 500 megahertz, which was dedicated to it, the Redis server is using 26 megahertz. It's using 26 MB of RAM out of the 256 MB allocated. And here is the IP address. So this IP address, so I'm going to use Redis over here, Redis CLI -H, and this particular IP, and then port is 20,001. Is it 2001 or 20,001 here? I can't see. Okay, is it good now? One more zero? Okay, good? Oh, okay, cool. Oh, okay, I can see here too. So now we are logged into the Redis server over the network, and we are going to say, set foo bar, because that's the best way to use Redis, and set HashiCorp and 2016. And so on. So Redis saves to its datatar, I think, after a few seconds or something, but we are going to make sure Redis saves right now, so I'm going to write save, and hopefully it saved, yes. Let's get out of here, and again, see the allocation. So the allocation is still running here. I want to see like whether Redis actually wrote something into the datatar. So Nomad, as I said, Nomad has like an API for seeing the file system. So you can use nomad fs command, and you basically get the allocation ID, which is like 128. And you will see that this is the file system of the allocation. So let's look at the Redis directory. So Redis local. So Redis has written something like mydump.rdb or something like that, and redis.conf. So now let's say that it's in the middle of the night, and you don't want this node to work anymore because there is some issue or something. And as an operator, you want to drain the node. That is, you don't want any more allocations to be running here, and Nomad to not schedule anything new. So let's get the node ID where this allocation was running. So the node ID starts with df. So I'm going to use this command, nomad node drain -enable df, and Nomad is asking me that are you sure that you want to drain this node? So I'm going to say yes, and that's it. So now Nomad should migrate the container, migrate the allocation. So let's see what is happening with the allocation. So since we said drain the node, Nomad sent an interrupt signal to the task. So Nomad first sends a SIGINT and waits for the task to shut down cleanly. And if the task doesn't shut down cleanly, Nomad will send a SIG term, and then it will basically forcefully kill the task. So we see that this allocation is no longer living. It's in a terminal state. So now let's go and see the status of the job. Nomad status, example. So we see that Nomad has stopped the allocation on the node which we drained and started the allocation on another node. And so now we have a new allocation which is running on the other node. And let's get the allocation details so that we know the IP address. Alloc status. Copied the wrong thing. What is it? 16. Okay, so there is a new IP, 10.10.11.81. So Redis CLI 81. So let's see if Nomad has transferred all the data. So I'm going to do key star. So there you go. So all the data that the other Redis allocation has written has been migrated by Nomad. And you can see that by introspecting the file system again. So it has moved the data, the snapshot file that Redis has written from the one node which is drained into this new node. So that's sticky volumes. So sticky volumes is really useful. Like if you're developing existing automations to move data of stateful applications which don't replicate themselves, right? If you're developing automation to move the data before you start the application again, so sticky volumes is good from that perspective. The other place where sticky volumes is good is like if you want the allocation to have some sort of data locality, like you want the allocation to be restarted on the same node as much as possible, right? So that's where sticky volumes, again, is useful. So that's pretty much it. Thank you. I think we are doing good on time, so. So if you have any questions, please feel free to ask, since we have like, I think 1 or 2 minutes more. Thanks.
Are there any constraints when the data is replicated because it can consume all the network and all the data?
Yeah. So we are still working on that aspect. Like we are going to put the replication part in some form of C groups in the near future. So if you have like a unbounded amount of data like going from one node to another, so you should be able to, as an operator, you should be able to say that use this much resources. It's not, the design there is not final yet. We wanted to get this feature out where we can move data, and once we see like how the community is using it, we will basically introduce some knobs in there for operators to say that limit the amount of resources. It's a very good question. Yeah.
So like if the old client node, for network reasons, can't reach the new client node, then the replication center fails.
Yeah.
It has to be worked from
Yeah.
New container created or data moved, new container created while the old container is still active?
So we do a blocking query on the node where the allocation has moved for the other allocation to actually die, and once it moves into the terminal state, only then the replication starts. Yeah. Cool. So the whole Nomad team is here. Alex, me, and Michael, we are hanging out here. Please come and talk to us. We would love to hear from you. Thanks.